All right, let's get back to work, okay? Now, in this notebook, we are talking about multiple linear regression, and the difference between multiple and simple linear regression is that for multiple linear regression, we are using a lot of X, right, to predict Y, okay? And when we do that, actually, when you are calling the method, it's basically the same, right? And after you get the model, you do the summary, you will have a lot of coefficients comes up, right? One coefficient for each of these X, okay? But basically, the mathematical relationship will become this one, right? And in this mathematical relationship, we can say that we actually can interpret the coefficient as the marginal effect of the corresponding X, okay? If X3 is increased by 1, the prediction of Y would increase by B3, right? Okay, so you basically can treat the coefficient as the marginal effect of X to Y, okay? But there's a caveat that I had told you at the end of next hour, the last hour, that the estimation of this coefficient are subject to a series of assumptions, okay? So in the real case, the assumption is very often breached, okay? So we cannot trust too much about the, if you only want, if you are very serious about the correctness of this coefficient, okay, you need to learn econometry. You need to learn the research method in depth, okay? Basically, there are a lot of ways to verify the assumption, to correct the assumption when they are breached, right? And that would take like maybe 2 or 3 semesters to cover that things, right? But in our purpose, we'll actually, instead of worry about the accuracy of each of these coefficients, our purpose is on the prediction itself, okay? So although we cannot trust too much about each of these individual coefficients, the overall prediction is basically okay, right? So for most of this assumption would not affect the prediction itself. It would affect the estimation of individual coefficient. But when you put the coefficient together, the prediction is still okay. Okay, so fortunately, for our business analytic purpose, we can use linear regression without worrying too much about all of these assumptions, which we cannot cover in our course. Okay, so we only worry about the prediction and the accuracy. Okay, that's precisely, we worry about the prediction, especially the accuracy of the prediction, and that's what we want to deal with in this hour. Okay. Okay. Let's go back to the slide first. There's an idea called the goodness of fit. Okay. The reason that we want to predict Y is because that Y varies, right? Okay. So in statistics, there is a measurement to measure the variation of a variable. It's called the variance. Okay, if you still remember that. Okay. So the way to calculate variance is that you have a Y bar, right? Y bar is actually this dot line, which is the average of Y. Okay. This is the average of Y, and the variance of Y is like how Y would vary along its own average, right? That's the variance of Y. Okay, so if we take the difference and square them and then sum it up. The reason that we need to do the square is because some of the error are negative, right? The actual value minus the average, some of them are positive. For example, this one, they are positive, right? And this one, they are negative, okay? And we don't want the positive and negative to if we do not use the square, kind of like all of this positive and negative, they will add up to 0, isn't it? Right? So when we are talking about the variance, usually we will like square the difference and sum them up, right? And actually, this SST, we can treat that as the total variance. T stand for total, right? So it's the total variance or total sum of square error, okay? The total variance in Y, okay? And if we estimate Y by this regression line, okay? The Y hat is actually this blue line, okay? As we can see that there's an intercept and there's a slope in X, right? So this is the regression line. Y hat is the regression line. And so this is the arrow. Take this point for example. This is the arrow between actual and the average of Y. And this is the arrow between actual and the prediction value of Y. Okay, which one is smaller? Yeah?
The pink line is the mean?
Yes. The pink line is the mean. Okay? The pink line is the mean. And the blue line is the regression line, right? So as you can see that if they are some correlation between X and Y, the arrow between the actual and the regression line tend to be smaller than the arrow between actual and the average of Y, right? Isn't it? Right? So some of the error, some of the variance in Y will be removed from, will be expanded by variable X, okay? Some of the variance of Y can be expanded by X, okay? Which means that if we use this the sum of square error, right? Which mean by is the square, the sum of square of this arrow, okay? So this thing is tend to be smaller than this thing, right? As we have explained, right? So this thing is smaller than this thing. So this term is actually like, this is larger, this is smaller, right? So 1 minus this fraction is actually the fraction of variance expanded by the model, okay? So there's the R square. When you look into the summary of a model, you will see that there is a thing called R square, okay? And the R square is actually, well, practically it represents the fraction of variance of Y that is like removed, that was reduced by the model, okay? If I do not have the model, I need to explain Y by its variance, by its average, right? Okay. If I use Y's average to predict Y, I will have this many error, okay? But if I use the regression line instead, okay, the error will reduce, right? And the amount of error reduced, okay, is the R square, okay? So this 75% of the variance within Y, okay, is expanded by the error, okay? So if I predict Y with the model, okay, the error, the variance will reduce to like from 100 to 25, okay? Because 75% of the variance in Y has already been controlled, has already been expanded by the model, okay? And that's why we want to use the model, right? Okay? See? If I do not use the regression line and I use the average, okay, the error tends to be larger, right? So when I use this regression line to estimate Y, I will have a smaller error compared with the average Y, okay? But I want to know how much, right? I want to know how good I am, right? So I do this fraction, okay? This R square calculated this way will represent the number of variance expanded by the model, okay? Which means that if I use the average of Y to predict, I will have sum of square error 100. But if I use the regression line, I will only have 25 because like 75% of the variance would be expanded by Y. So using model to do prediction is better, right? And the higher the R square is, the better the model is, right? Sometimes you have R square like 0.2, right? And now the 0.2, it means that they only explain like 20% of the variance in Y, okay? You have R square 0.9, which means it's a very good model that explains like 90% of the variance in Y. See that? Okay, so R square is a way to measure the goodness of fit, okay? How well the model fit the data, okay? Sorry?
R square will never be more than 1.
Yes, yes. It would always be between 0 and 1, okay? Because it's a fraction, right? It is a fraction. Any more questions?
Professor, so what is the acceptable range of R square in reality for us to assess a model is good?
Yeah, that is a very difficult question. Well, it depends on which area you're working on, right? If you are working on some engineering department, usually the R square is very high, okay? But for social science, for business, for human resource especially, the R square tend to be very small, right? Like, I think in some academic journal, I even see some R square as low as like 0.15. Okay, so it depends on which discipline you are working on. In some discipline, prediction is like very difficult, and their R square is low. Okay, so there is no fixed threshold that's saying that this R square is acceptable, that R square is not acceptable. It really depends on your research question. That answer your question? There is no absolute threshold that R square need to like exceed this threshold. No, there's no such thing. Okay, I even saw a R square as low as like less than 0.1, and it also published in a very good journal. Right? So there is no like fixed threshold of R square. Okay, but that gives you a measurement of how good the model is, how good the model fit the data. Okay. So R square is one error measurement. There's another type of error measure. It's like kind of more straightforward. For example, you can use actually like MAE, which is the difference, and you use the absolute value, right? And just divide them by n, right? So this is kind of like the average error, okay? So if you are using average error to measure the accuracy, okay, there are pros and cons, right? The benefit of using average error is that it's the same unit as y, right? If y is dollar, then if you calculate error this way, the average error is also dollar. If y, the unit of y is like $1 million, then the unit here is $1 million. And the disadvantage is that there's no there's no range of average error, right? Different model, you will see that different unit of error, right? It's unlike R square. The R square is kind of like, no matter what type of data you're working on, it's always between 0 and 1, right? So if you want to do comparison across different models, R square is better, right? So, but the average error has the advantage that you can get a very intuitive idea about, well, the average error of the model when I use this model to do prediction. Okay? That's the two-way of measuring accuracy. Okay? So measuring error is the same thing as measuring accuracy, right? It's the two sides of the same coin, right? Get it? Okay. Okay, so as we say that when we do the build the model and we check the model summary, the R square is automatically calculated for you. Okay? So you don't need to calculate R square by yourself. Okay? You build the model and along with the coefficient. Okay? I think, well, it's dying. Okay, so you don't need to calculate R square by yourself. Okay, you go with the model. Okay, so however, I just like I still like, because we know the according to this equation, I also do the calculation here. Okay. So as you can see that this is just to verify that the R square that we calculate 0.75089, right? It's the same, exactly the same as this one, right? Okay. So but there's a problem here. Okay, there's a problem here. See, now we are talking about the measurement accuracy in the training data, right? Okay? Because I do not give them new data, right? So this accuracy measurement, okay, is actually the accuracy measurement when the model is predicting the training data. But that is usually not, that is not what we want, right? In business analytics, okay? In business analytics, we care about the accuracy of the model when we use the model on some new data, right? So we use this existing data to build a model, and come with the model there is R square. But that R square is actually the accuracy using this model to, right, to against the training data. But what we really want is that when we use new data to test the model, we want to know its prediction, its accuracy, right? That's what we really want to know. So in order to do that, before we build the model, we already reserve some of the data, right, for accuracy measurement, right? Now we can use it, okay? Now we can use it. So so here we can like do the prediction, and this is the model, right? Okay, and I use TS as the data, right? So the predict here would actually be the prediction on the testing data, right? So this is the y hat, right, on the testing data. So basically, if I follow the mathematics here, right? Follow the math here. For example, when I want to, I know the prediction value, I know the actual value, right? So here first of all, I get the prediction value, and this is, what is it? This is y hat, right? Right? And this is y, the actual y, right? So the different square sum. So this is sum of square error. Testing. Okay? And for the sum of square total, you can see that this is the here, and in between. So we can calculate the SSE and calculate R square. Okay? So we can compare them. As you can see that the testing R square is actually lower than the training R square. Usually this is the way. Okay? When I use the model to, when I check the model accuracy against the training data, it tends to perform better, right? Because the model is training out of this data, right? So if I use the model on some reserved data, some testing data, and this is usually the R square that we really care, right? Actually, you can also calculate the RMSE, which is the average error, okay? As you can see that for training data, the RMSE is like 0.09, and this thing is higher, right? This is 90 and this is 95. See that? Okay. So as I told you that the R square and RMSE, they are the same thing. They are the two sides of the same coin, right? When you have a higher R square, you will have a lower average error. Okay? When you have a lower R square, you will have a higher average error. Okay? And what matters is the accuracy measurement on the testing data. Okay? That is important in our business analytics. Okay? See that? Okay, so this is the way that we measure the accuracy of a model. Okay? And the way that we evaluate the accuracy of the model by using some reserving testing data. Got it? Okay? So usually when you do linear regression on a business analytic purpose, what you really need to do is to, like, first of all, prepare the data set. Okay, that's the first step, right? Second thing, you need to split the data set into training and testing. Okay? Prepare the data, split it into training and testing. And then you build a model by the training data. Okay? And actually come with the model, you already have the accuracy of the model on the training data itself. You don't really need to do this calculation because this number is already here. Okay? What you really need to do is, like, do it by yourself. Is actually you need to do this code chunk. Okay? You actually can copy this code chunk and use it in your own application, right? So you really need to like do the prediction using this testing data and calculate the R square again, okay? And that is the R square that we really want, okay? Problem? So in business analytics, it's that simple, okay? First step, prepare the data. Second step, split the data. Third, make the model. And the fourth, do prediction, okay? That's what we want to do. You don't really need to do the plotting. You don't really need to do that. And most of the time, you don't really need to care about too much about the p-value, the significance type of thing. Okay? However, that could be important when you are doing inferential statistic as well as research method. Okay? So as I told you, there's a discussion here, right? Okay. And this is kind of like your homework today, right? Your homework is like we have 2 notebooks, right? I want you to finish the exercise, do the discussion, and kind of knit the notebook by yourself and upload them. Okay, so it's not too difficult, right? So let's do the discussion here, right? So in the aspects of business, which of the following do we care most? What do you say? Significance? Anyone else has a different opinion? Yeah, actually, in business, we care about the coefficient because the coefficient has the implication that it indicates the marginal effect of X to Y, right? For example, if this X is my advertisement expense, right? And I want to know that for every million advertisement expense, how is my advertisement would affect my revenue, right? See, so if I know that 1 million of advertisement would raise my revenue by 20 million, right? That would be good, right? So in that sense, I would care about the correctness of the coefficient, okay? But as I told you that the estimation of coefficient, usually you cannot just simply do a regression like this. Okay, that would you need to care about a lot of assumption. Okay, I don't really have time to go over all of the assumption, but one of these assumptions is that in order to have I do not have time to cover this coefficient as random variable type of things. This is to like explain what it means by p-value. Okay, and I would suggest you skip this one. Okay, when you do your homework, don't need to do the section C, right? Okay, because that I do not really have time to explain that, and that is not very important to us anyway. Okay. What is really important is that, as I told you, that if you care about the correctness of each of these individual coefficients, okay, then you need to care about a lot of problems. One of the problems is called collinearity, which means that one of the assumptions to make sure that the coefficient is unbiased, okay, one of the assumptions is that there should be no correlation among the x, okay, which means that because you are explaining the variance of y by x, right? So if the x by itself has a very high correlation among them, I mean that if there are a high correlation among this x, okay, as we will see in this example, right? The CH4 and N2O, their correlation is as high as 0.9, okay, and this one is even higher, right? 0.98. See that between CO2 and NO2, right? Because they are very high correlation among the x, then their individual coefficient might be biased. Okay, you cannot trust the individual coefficient if they are high correlation among the x. Okay, this is one of the assumptions that need to hold before you can trust the coefficient. But as I told you, fortunately, that will not affect the prediction value. Okay, you cannot trust the individual coefficient, but you can still trust the prediction as a whole. You just cannot use them. You cannot use each individual coefficient as the marginal effect, right? And if you really want to evaluate coefficient, as I told you, you actually need to take a course of like 2 or 3 semester econometry type of thing. It's not easy, actually. It's not easy. Actually, most of the economical literature dealing with all of these problems. Okay. So as an example, I just want to show you that when they have this collinearity problem, collinearity means that they are correlation among the independent variables, right? Okay. For example, like this one, then you can no longer trust the coefficient, right? So one way to deal with it is you can actually like adjust the model spec, right? You can see that they are CO2 and N2O, they are very high correlated with each other, right? So you can manually like remove some of the highly correlated independent variable out of the model. Okay. For example, if I originally we have 8 variable, right? Independent variable. Now I remove 4 of them, and I build a model again. Okay. And this 4 model, because I inspect the correlation manually and pick them by manually, right? So Now, because their correlation is low, right? So I can trust the individual coefficient better. Okay. As you can see that after I remove 4 variables out of the model spec, the R square drop, right, from 75 to 726, right? So it only like dropped like 2.5 percent, right? But this model, although it has a lower R square, it actually has a better validity on the coefficient, right? So in this sense, this model will be better than the first model, which actually has a higher R square, but you cannot trust the coefficient, okay? But actually, collinearity is just one of the assumptions that could bias your coefficient, okay? It's just one of the assumptions. There are a lot of assumptions, right? For example, the error must be independent of all of the independent variables. The data point has to be independent from each other, right? As I told you, that if you want to learn, if you are very serious about the regression coefficient, you need to take the course for like 3 semesters in a row, right, before you can do that. And we don't have time to do that. What I can tell you is that in our course, most of the time we only want to build model, and we only want to use the model to do prediction, okay? And if that is the purpose, then you don't need to worry about too much about this collinearity, this independence error, that type of some endogeneity. Sometimes if you miss the problem is there are too many independent variables, right? Sometimes you miss some of the important variable would also cause the bias in your coefficient. So there are so many different things that will affect the correctness of your individual coefficient. So you need to treat them very carefully, okay? So simply by reading this equation, you can say that this coefficient represents the marginal effect of F3, right? But in order to estimate B3 very seriously, take a lot of work, okay? And that is not what we can do. We don't have time to cover that in our class, okay? Get the point? Now let me get back to the slides. So there are some caveats, okay? In business analytics, in R, when we're using regression only for prediction, actually the process is quite simple, right? Prepare the data set, split the data set, use training data to build a model, right? Do the prediction. That's it. Okay? That's it. Simply just put whatever variable you can use into the model. Don't worry about the collinearity problem. Okay? If you do care about the marginal effect, then you had better consult some of the technical people, right? Don't take it for granted that the coefficient represents the marginal effect. It's dangerous, okay? And then, as I say, that there are a lot of problems because the bias estimation, right? Collinearity is caused by too many too many x, but we'll have problem. If you have too few x, some of the x, if you do not include it, some of the important x, if you miss them, in your model, it will also bias your estimation. So it's quite difficult. So there are sometimes there are time, spatial, organizational dependency among the data point. That will also bias your estimation. Okay, so you really need to learn a lot of things before you can have a better. I have some reference here. Okay, that I do not have time to cover. Okay, okay, and so today in 3 hours we only have time to give you an idea about how we would use prediction model in the context of business analytics. Okay, so today we discussed the most simplest linear model, which is the we discussed most simple model, linear regression model, right, to predict the value. Okay, we learned about how to do that in the R environment. Okay, and actually simply by using it to build model, to do prediction, to measure the correctness of the model is not too difficult. Okay, but be careful, right? Okay, although the equation of linear model implies that coefficient is the marginal effect of x, that need to be applied very, very carefully. Otherwise, you will do a lot of problem. You might run into a lot of problem. Okay. Okay. That's all for today. Any question? No?
Professor,
Yes?
how can we handle the missing value in our data set?
The missing
Value in our data set, if we want to use the regression.
Oh, if you want to use a regression, if a data point has a missing value, that data point will be removed. It would not use. It would not accept missing value. Which means that the data you use to train your linear regression model cannot have missing data. Okay, so for a linear model, all of the data must exist. If there is one single value is missing, the entire data point cannot be used. See what I mean? Okay. Some methods do not have this limitation. For example, if we are using decision tree, it can handle missing value. There's no problem. But linear regression model cannot do that. Okay? Question? Any more? Okay, that's all for today. And next week we will teach the other prediction model, which is the logistic regression model for predicting probability. Okay? Okay? And predicting probability is actually more important than predicting value in business application. Right? In another word, knowing that probability that a customer will buy or will not buy, okay, is usually much more important than how much he will buy. Okay? So I'll see you next week. Okay. Right.
那我们在做一些商业决策的时候，他们应该要怎么去看这张图，然后看到一些可能 A 跟 B 之间的相关性？ 然后去判断他们的接下来的下一步。如果他们比较，
如果你真的要确认某一些变数之间的因果关系，那有一套特别的方法，这样就一样哦，就像是我刚刚讲的，在你有一些其他的课程，像是在计量经济里面，那它就有一个特别的章节，这样，告诉你说你要怎么样去确认因果关系。然后确认因果关系其实不是很容易的，
不能只看线性回归这种单一的分析。
通常你要确认因果关系是需要做实验的，意思是说你只是拿一些 observational data，没有办法让你确认因果关系的。
但我比较想请问的是，比如说我们之前在工作的时候，假设一个门市，然后会有顾客的很多资料，像你给的他放的资料一样，